Yeah. So, good evening, everyone. Welcome to week number 10 of NPTL Discrete Mathematics course. My name is Bhavya, and today's topic of this week's topic is Inclusion Exclusion Principle. And we'll be just revisiting some of the concepts there, but mainly what we are doing is will be solving a few problems related to the Inclusion Exclusion Principle and derangements. Okay. So, what is the inclusion exclusion principle? Well, briefly, inclusion exclusion principle helps us study cases when we need to count the size of sets. Okay, when sets are not necessarily disjoint with each other. For example, as you can see in this diagram, A and B actually overlap with each other. So, if we study a case where this we have two sets A and B, and let's say the size of A is 10 and the size of B is 15, let's say. Okay. Then if I ask you the question like, what is the total number of elements in neither A or B, right? Or in other words, what is the size of A union B? Then of course, I mean, you'll just say, oh, it's just 10 plus 15, and it's 25. You will directly say that. But let's say these the image, the diagram does not look like this. Okay, the scenario is slightly different. Rather, instead of being separate, they are joined in between. Okay, and these area, okay, which is nothing but A intersection B, actually represents that some of the elements are shared together. So if you say what is A union B now, okay, and if you ask the same question again, what is A union B? A union B is equal to 25 will not be true anymore. Since A is of size 10 and B is of size 15, and since there are some elements that are sitting in between, so if I say 10 plus 15 is your answer, then it will definitely be wrong because you are over counting these guys. So these guys are over counted. Okay, let me write it better. These guys are over counted, right? So to handle cases like these, we study the inclusion exclusion principle, right? Now let us look at the simple inclusion exclusion principle on two sets. Okay, let's say there are two sets A and B. Okay, and this green area, as you can see, is A intersection B. So what is the size of A union B? It is size of A plus size of B minus A intersection B. So this is removing the overcounting. Since you are counting it twice, this area A intersection with this green area, I'm removing it once to make it proper. And what if there are three sets? In the case of three sets, we'll look at the case when there are more sets. But this is the simple high school method, okay, of inclusion exclusion principle. What if A union B union C? Then it's size of A plus size of B plus size of C minus the sum of sizes for intersections of two sets each, that is A intersection B plus A intersection C plus B intersection C, plus, now as you can see, observe that the signs are alternating. Okay, plus then minus then plus. Okay, A intersection B intersection C. Now how this comes about, I'll not explain, it's there in the lectures, but we'll just solve a few problems. Okay, and the first few problems are rather simple. It is just a direct application of inclusion exclusion. Okay, yeah, so the question is as follows. Suppose that in a basket of 100 apples, okay, we know that the basket contains 100 apples, there are 20 that have worms in them, 15 that have bruises. Okay, only those apples with neither worms nor bruises can be sold. If there are 10 bruised apples that have worms in them, how many apples can be sold? That is what they are asking. Okay, now we can write the question as we can think of the question as follows. There are 100 apples in the basket, right? So let's say this rectangle represents the basket. 20 have worms in them. So let W denote, okay, set of apples with worms. Okay, and what do we know? We know that the number of apples that have worms is 20. So the size of the set is 20. And 15 that have bruises. So B is set of apples with bruises. And set B, okay, may not be this way, because there could be apples that are both containing worms and are bruised also. So this is B, let's say. Okay, so what do we know about B? Size of B is 15 have bruises, right? 15. Only those apples with neither worms nor bruises can be sold. So in the diagram, can you recognize what is the set of apples that have neither worms nor bruises? Okay, these are the ones with worms, and these are the ones with bruises. Everything outside this particular set is what we want, right? So this is the area with neither worms nor bruises. That is nothing but 100. Okay, that is the total universe size, total number of apples, minus the ones which have either worms or bruises, that is worm union bruises. I hope this is clear. Okay, so from the total 100, we are just subtracting this union of W and B. So now the problem reduces to finding this union. Okay, as soon as we find the size of the union, we get the number of worms that have neither the number of apples that have neither worms nor bruises. Okay, so this is the basic idea. Now additionally, they are also saying if there are 10 bruised apples that have worms in them. What does it mean? What are apples that have worms in them? Okay, there are 10 bruised apples that have worms in them, meaning worms intersection bruises. Okay, the apples which have both worms and bruises. Okay, this area is nothing but the size is nothing but 10. There are 10 worms. Sorry, 10 apples. I'm just saying worms over and over. Yeah. So now what we can do, we can just use the inclusion exclusion principle directly by principle of inclusion exclusion, which is also popularly called PIE, by the way. Okay, principle of inclusion exclusion. We have that the size of W union B is nothing but the size of W plus the size of B. Okay, Divya has given 55. Okay, let's see, Divya, minus W intersection B, which is equal to 20 plus 15 minus W intersection B is 10, which is 35 minus 10, which is equal to 25. Is it not? So then what do you have? Then what did we need? We wanted 100 minus W union B. So sorry, sir. Oh, okay. Yeah. So need W 100 minus W union B, which is 100 minus 25, which is equal to 75. Okay. Yeah, Divya, it's 75. Good. So I hope it's clear so far. So if not, please let me know. So this area, this red area, has the size 75. Okay. So what is another word for 100 minus W union B? I mean, what is another way to show it in terms of set theoretical notation? The universe minus the union. So this is also what is called W, same as W union B complement, right? Or it is also equal to W complement intersection B complement by De Morgan's law. I mean, we are going to use this fact later on, so I'm just mentioning it right away. But even if you don't understand why this is the case, then it's not a problem. We'll handle it later. Okay, but I hope the general idea is clear. Okay, so yeah, let's move on. Here is the question. I would like you guys to try it. Now, this is principle of inclusion exclusion on 3 sets instead of 2. Okay. So the question says there are 350 farmers in a large region. Okay. 260 farm beetroot, 260 of them farm beetroot, 100 farm carrot, 70 farm radish. Okay. 40 farm beetroot and radish, 40 farm carrot and radish, and 30 farm beetroot and carrot. Determine the number of farmers that farm beetroot, carrot, and radish. Okay. So as long as you remember the formula, I'll write the formula just in case again. The formula for A union B union C, cardinality of A union is A plus B plus C minus A intersection B plus size of A intersection C plus size of B intersection C plus A intersection B intersection C. Okay, this is the formula. Now try to extrapolate this particular question using this formula of inclusion and exclusion for three sets. Okay. Also, I would say assume that each farmer, you know that there is no farmer that does not farm either of the three vegetables. Okay, every farmer farms at least beetroot or carrot or radish. In case you're if in case you're wondering what the universe is, and so please try this question. Again, if there is confusion in relating to the previous question, I'm telling you, every farmer should assume that every farmer should farm at least one of these three variables. Okay, Akanksha says 30. Okay, good. Let's see whether it's correct or not. Okay, let's wait for some more time. Okay, so yeah, let's look at the answer. But if you're in the process of trying this question, please continue. So the question says there are 350 farmers in the large region. So I told you, just assume, okay, in this particular case that each farmer actually farms something or the other. So okay, so what are the vegetables? Beetroot, carrot, and radish. Okay, B, C, R represent set of farmers farming beetroot, carrot, radish, respectively. Okay, so this is B, this is C, this is R. Now, since I told you, there are 350 farmers and all of them farm either beetroot, carrot, or radish. So already we have that, the total number of farmers. Okay, the total number of farmers who farm beetroot, carrot, or radish is 350. Okay, so in other words, B union C union R is 350. This is given. What else is given? 260 farm beetroot, 100 farm carrot, and 70 farm radish. So number of people who farm beetroot, carrot, radish are how much? 260, 100, 70. Is it not? Next, 40 farm beetroot radish, 40 farm carrot radish, 30 farm beetroot carrot. B intersection C, C intersection R, and R intersection C are respectively 40, 40, 30. Okay, and finally, what are they saying? Third, okay, determine the number of farmers that farm beetroot, carrot, and radish. So if you observe properly in the diagram, this is what we want. This is B intersection C intersection. This is what we need. Those farmers which farm all three, beetroot, carrot, and radish. Right? And now, okay, now B intersection C intersection R is what we don't know. But how do we find this? Well, all these terms are actually contained in the inclusion exclusion principle, the formula of inclusion exclusion principle, and from there we can obtain this. How? We know that B, okay, union C union R is nothing but size of B plus size of C plus size of R, okay, and minus B intersection R, C intersection, and so on, B intersection R plus C intersection R plus R intersection C, okay, plus B intersection C intersection R. Now on the left hand side, B union C union R is nothing but 350, okay, and B plus C plus R is 260 plus 100 plus 70, right? And here what do we have? 40 plus 40 plus 30. Now this is nothing but 40 plus 40 is 80, 80 plus 30 is 110 plus B intersection C intersection R. Okay. Now 350 equals this is some 360 plus 70 would be 430, I guess, right? Tell me if it's wrong. Okay, 430 minus 110 plus B intersection C intersection R, and which is equal to, which means that 350 minus this, how much do you get? 320 equals B intersection C intersection R, which is equal to 30. So yeah, Akanksha, it's 30. Good, correct. So yeah, I mean, the simple formula for inclusion exclusion principle can be used in this way. Okay, and this is for 3 sets. So now use the same. I hope that is clear. Okay, please let me know. We just find out what the size of these sets are. Okay, what they represent, and the rest is just plugging in the formula. But you can try this other question also. Okay, it's of a similar flavor. Three sets are given, and you can try this. Mm, which time is that? Yeah, okay. So the question says the following: there are 1,000 applicants for a mountain climbing trip in the Himalayas. 450 get altitude sickness, 622 are not in good shape, 30 have allergies. Then now what you can do is you can immediately tell what the sets represent, right? So this, let's say altitude sickness is A, then number of people who get altitude sickness is 450, and let's say people who are not in good shape are um, let's say S, okay, not in shape, SNS is equal to 622, and 30 have allergies, which is nothing but okay, allergies. Okay, okay. Let me call them ABC. That's better, I think. A, B, C, and C is allergies. 30 have allergies. Okay, an applicant qualifies if and only if this applicant does not get altitude sickness, is in good shape, and does not have allergies. What does it mean? It means it's not in A, not in B, not in C also. Because if it was in one of them, then either they would be altitude sick, or they were not in good shape, or they do not have allergies. Okay. So if this is altitude sickness, this is they are not in good shape and they have allergies, then these people, okay, outside are the people who we want. Okay, those who qualify. So the remaining are just extrapolation. So 11 applicants who get altitude sickness are not in good enough shape. So A intersection B is nothing but 111. 14 who get altitude sickness have allergies. So A intersection C is 14. 18 who are not in good enough shape and have allergies. So B intersection C is 18. And 9 who get altitude sickness are not in good shape and have allergies. So finally we've even got A intersection B intersection C, which is equal to 9. So now what do you want? We want this region. And what are the total number of applicants? 1000. So 1000 is the size of our universal set. So finally, what do you want? Need 1000 minus A union B union C. So now this is what we want. Now we just need to apply the principle of inclusion and exclusion. So use the formula and please let me know what the answer is. Try your hand at it. Okay, Divya says 137. Okay. Okay. Let's see. Uh, so let's open this up. A union B union C. Okay. Now, by the inclusion exclusion principle (PIE), um, we just add those on single sets, and then comes the pair of sets. We subtract them. 1 plus 14 plus 18, and then we add the final 9, which is 2, 5, 5, 10. Please let me know if there is a mistake. 1, 1102 probably, minus 111 plus 14 plus 8. So let's add this first. So 14 plus 18, okay, is 12, 32. Okay. Now 32 plus 111 is 143 plus 9, which is equal to okay, 143 plus 9. So 1102 minus 143 is nothing but 12 minus 3 is 9. 9 minus 4 is 5, and 10 minus 1 is 959, plus 9 is 18, 6, 968. And how many applicants are there? Number of applicants equals 1000 minus 968. So okay, let's just use a calculator for that. Oh. Oh, from the calendar, sorry. 1000 minus 968, 32. Okay, Divya, I'm getting 32. What did you say? 137. Okay, so maybe I made a mistake here. Okay, I'll just plug it into the calculator completely. 450, 622, 30. 3, 622, 30. 1102. Yeah, correct. Minus 143. So, okay, let's verify this. 111 plus 14. This should be correct. Yeah, I think so. So there shouldn't be anything wrong with this. Plus 9. Okay, so let's just do minus 142. 3 minus 143 plus 9. 968. Oh yeah, this is correct. So 1000 minus 968 is 32. Yeah. So yeah, I think 32 is the answer, Divya. But please let me know if I made a mistake here. Okay. Others also, like if I messed up the calculation, then please let me know. Okay, Divya. Okay, Bhumika also says 32. Then probably 32 is correct. Okay, good, Bhumika. Yeah, okay, Divya. Okay, please check it offline. Yeah, anyway, the answer is 32. So, yeah, now that we know some of the application of inclusion exclusion, okay, I hope everything is clear with everyone, but please stop me. Okay. Now, we'll look at the generalization of inclusion exclusion principle, right? That is what we are mostly focused in. Now, this is extremely useful, extremely useful in counting. And I mean, inclusion exclusion principle in general is extremely useful in all sorts of places. like especially pure mathematics and theoretical computer science. If we need to count things, then it is applicable left and right. So we'll see those applications now. So let's look at the generalized pigeonhole principle. All right. So let's say C1, C2 till Ck are events. Okay. An event is, whether some particular incident occurs or not. That is an event. So let's say C1, C2 till Ck are events. Okay. And we need to find the number of ways that the event when C1, C2, Ck will not occur. In such kind of cases, we will be using the generalized inclusion exclusion principle. Okay, if we need to, we need to translate in a way that all these events together will not occur. Okay, in other words, if you see them as sets, they are nothing but C1 complement, which means C1 does not occur, intersection C2 complement, intersection C3 complement, and so on till Ck complement. The number of ways in which C1 does not occur, C2 does not occur, and so on. So finding such kind of values is where inclusion exclusion principle is extremely useful. And n of C1 shows the number of ways event C1 occurs, n of C2 means number of ways event C2 occurs, and so on till some Ck, right? So what is n? Just n is total number of ways C1 occurs or C2 occurs or C3 occurs, and so on. In other words, it is just the union of all the events, union of all the sets which represent the conditions. Okay, now, this is done in the lectures also. This is what we need to find. C1 does not occur, C2 does not occur, and so on. And n minus all the single sets, all the single events, n of C1 plus n of C2 and so on, plus we can already see the connection with the normal simple inclusion exclusion principle, right? Two sets, C1 C2 C1 C3 and so on, and then for 3 sets and 4 sets and so on until all the key sets n of C1 plus C2 plus C3 plus Ck. I mean, this plus may be minus also, depending on what the number of k is. Okay, this is plus or minus. Okay, but anyways, this is the generalized inclusion exclusion principle. Please keep this in mind. Okay, now we'll see an application which was finding the number of solutions for equations. Okay, and the question says the following: how many solutions does the equation x1 plus x2 plus x3 equals 13 have, where x1 plus x2, x1, x2, x3 are non-negative integers less than 6? So x1, x2, x3 are non-negative integers less than 6. This is our constraint. So before I move on to solving this, can you think about the case when this constraint was not there? If the question was, x1 plus x2 plus x3 equals 13, what is the number of solutions when x1 is greater than or equal to x1? They are just non-negative, right? x2, x3 are non-negative, or in other words, greater than or equal to 0. That is, the constraint is not there, that it is at most 6. Then how do we solve this? So can you, this was done in the lectures previously, but I just want, what are we going to use? What technique are we going to use to solve this? We've seen this before, in one of the problem 15C2. 15C2, yeah, I think that's correct, yeah. Now what logic did you use, Akanksha, for that? Yeah, that's correct.
So sticks and the stones.
Exactly. Sticks and stones, or stars and bars, and that there are other interesting names for it also. But yeah, sticks and stones. The idea is that, we used was that, oh, okay, let's say there are 13 stones, okay, which are ones in our case: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 stones, which is nothing but um, the letter one, the number one for our case, okay, 1, 1, 1, and so on. These are my stones. Now what do? I take sticks and separate them like this. In how many ways? Okay, and when I separate them like this, I can already see that, this means x1 is equal to 4, x2 is equal to 3, x3 equals 1, 2, 3, 4, 5, 6, 6, and x1 plus x2 plus x3 equals 13. Right, this is one way to partition it. Another way to partition it would be like taking two sticks like this and separating the stones. In any case, they will add up to 13, which means they will satisfy this particular equation. So the number of solutions to this equation, number of solutions, okay, is, okay, equal to number of ways to partition 13 stones with 2 sticks, right? Or 2 stones are 36, which is nothing but 3 partitions. And the formula is n plus r, okay, minus 1, choose n. There is an dual formula also, choose r minus 1, but this is also works. So n plus r minus 1, choose n, okay, where n is the number of stones and r is the number of partitions. So n plus r minus 1 is 13 plus 3 minus 1, choose n, 13, okay, which is equal to 16 minus 1 is 15, choose 13. This is your answer. Okay, good. Now why did I ask this question actually? So remember this, we are going to be using this a lot also. So why did I ask this question? Now when we include the constraint, we'll be using that fact. Okay, so recall, yeah, let's see, x1 plus x2 plus x3 equals 13, number of solutions for this, where x1, x2, x3, okay, are non-negative integers less than 6. Okay, what we need is, we always need to find this n of c1, c2, c3 bar. Okay, now non-negative integers. So if this represents that the solutions when x is less than 6, x1 is less than 6, x2 is less than 6, and x3 is less than 6, solutions when these is the case, then c1, c2, c3 will represent when it is greater than or equal to 6. That is the idea. So c1, okay, is the number of solutions when, okay, x1 is at least 6, greater than or equal to 6, so that the complement will be x1 is less than 6, okay, and c2 is the number of solutions when x2 is at least 6, and similarly c3 is the number of solution when x3 is at least 6. Okay, so now what is this? This is nothing but number of solutions when x1 is not at least 6, which is nothing but x1 is less than 6. Numbers and c2 bar, which means x2 is less than 6, and c3 bar, which means x3 is also less than 6. That is the logic. Okay, this is this requires some thought, but please let me know if you want me to explain this once again. Okay, the idea is that when we calculate the complements, okay, we exactly get what we want, whatever the question is asking. Number of solutions when x1, x2, x3 are all at most 6. Okay, now why are we finding c1, c2, c3? Because the formula says so. We know that c1 bar, c2 bar, c3 bar, n, okay, of c1 is nothing but n minus n of c1 plus n of c2 plus n of c3 plus n of c1, c2 plus n of c1, c3 plus n of c2, c3 plus n of c1, c2, c3. Oh, sorry, minus. This is why we are doing all this surface. Okay, so let's go serially. First, we want to find c1 and n of c1. So n of c1 is number of solutions. Oh, sorry, n. Okay, let me write n of c1, n of c2, n of c3 here. Number of solutions when x is at least 6. So x1 plus x2 plus x3 is equal to 13. Okay, and x1 is at least 6. If you do that, then x1 can be thought of, you may have seen it in the lecture, x1 may be thought of as x prime plus 6, where x1 is at least 0, because x1 was at least 6. And treat this x1 and x prime as same. So in other words, it's the same as subtracting 6 on both the sides, because plus 6 will go that side and it will be 13 minus 6. I mean, that is the logic here. But you don't need to remember all that. Just remember, since x1 is greater than or equal to 6, we can subtract 6 on both the sides, is equivalent to solving x1 plus x2 plus x3 equals 13 minus 6, which is nothing but 7. Or I'll write 13 minus 6, which is equal to 7. Now, what is the answer to this, where x1, x2, x3 are greater than or equal to 0? Well, again, we'll use the sticks and stones formula, right? N stones are partitions, okay, and number of partitions are 3, okay. N plus r minus 1, choose n, which is equal to what is n here? 7 plus r, which is 3, minus 1, choose 7, okay, which is equal to 10 minus 1, choose 7, which is equal to 9, choose 7, okay, which is 9 times 8 times okay, 7 factorial will cancel out, then 2 factorial. So this is nothing but 4s are 8, 4 9s are 36. Okay, now then similarly, you will see that the case for C2 and C3 is also same, because what we are doing is essentially x2 is, instead of x1 is at least 6, we'll do x2 is at least 6. Okay, x2 is at least 6. So same thing holds, and then you have 36, and n of C3 is also equal to 36. Okay, now it's just the same process over and over again. So next we have n of C1, C2 is when x1 plus x2 plus x3 is equal to 13. Now both x1 and x2 are at least 6, which means we can subtract 6 two times on the right hand side, and it will be equivalent to solving that case. This is equivalent to solving x1 plus x2 plus x3 equals 13 minus 6 minus 6, which is equal to 1, right? Which is equal to 1. And yeah, so we're going to solve this where x1, x2, x3 is at least 0. But I mean, how many ways are there to solve this equation? x1, x2, x3, the total should be 1 and they are at least 0. So the first way is 0 1 0. The second way, sorry, 1 0 0. Second way is 0 1 0 and 0 0 1. I mean, you can use this, you can do this using star and bar. I mean, the stones and sticks also, but I mean, this is intuitively simple, right? So 3 ways. Therefore, n of C1 C2 is 3, and so is n of C2 C3, and so is n of C1 C3. Okay. So finally, n of C1 C2 C3 is number of ways. This is nothing but number of ways in which C1 C2 C3 number of ways, number of solutions for x1 plus x2 plus x3 equals 13. Okay, when x1, x2, x3 is at least 6, all three of them are at least 6. But this is not possible, right? It is not possible to find a solution, because if all of them are at least 6, then their sum, but x1 plus x2 plus x3, then their sum will be at least 6 plus 6 plus 3, 6 plus 6 plus 3, 6, which is nothing but 18. So no solution. So number of solutions equals 0. Therefore, n of C1, C2, C3 equals 0. Okay. And so using PIE, we have that n of C1 bar, C2 bar, C3 bar is equal to n of C1, n. Okay. So what is n here? N is the one without the constraints. That is the total number of solutions. Okay, which is 15 choose 3. Okay, which is 15 choose 3. Okay, minus C1, C2, C3, which is 36 times 3 plus all this is 3, right? 3 times 3. I'm writing 3 times 3 because it's identical for all. So it's plus 0 minus 0. Now what is 15 choose 3? 15 choose 3 is nothing but 15 times 14 times 13 by 3 factorial, which is nothing but 6. Now, yeah, 6 minus, okay, but so you can solve this and then get your answer. But this is the general idea and how you will use the principle of inclusion exclusion. So please let me know if there is a problem here. So in case of finding solutions for equations. Now we are going to step up this idea, okay, and solve a few problems. So the question is simple: how many ways are there to distribute 6 different toys? Okay, what is the problem? Is the charge over? Okay, how many ways are there to distribute 6 different toys to 3 different children such that each child gets at least one toy. I mean, such are the kind of questions that principle of inclusion exclusion helps in. As soon as you see something like at least one toy or at least two and so on, then inclusion exclusion without a doubt. And how do you achieve this? Well, always think of the opposite case. What is the opposite of at least one toy? So, opposite of at least one toy, like we did in the previous, we call that it was at least, it was, yeah, at least 6. We at most 6. We made it at least 6, right? So similarly, suppose at least, opposite of at least one toy is greater than equal to one toy is less than one toy. Is less than one toy. Okay. What is less than one toy? Which is nothing but 0 toy. Because like toy is cannot be, you cannot say half a toy or 1.5, 0.5, 0.3 toy or something like that. Less than one toy is 0 toys. So this is our conditions. Always remember this. Always look for the opposite case. Okay. So these are our conditions, 0 toys. So what do I mean by this is the condition? C1 will be, okay, how many children are there? There are 3 children. So child 1 gets 0 toy. C2 is child 2 gets 0 toys. C3 is child 3 gets 0 toys. As always, what do we need? We need number of children, number of ways in which C1 bar, C2 bar, C3 bar, which is child 1 gets at least one toy, child 2 at least one toy. Since we know that opposite of 0 toy is at least one toy, C3 is child 3 gets at least one toy. This is the idea. Okay. Now the rest you know how to do. N of C1 bar, C2 bar, C3 bar is equal to N minus N of C1 plus N of C2 plus N of C3 minus N of C1 C2 plus N of C1 C3 plus N of C2 C3 minus N of C1 C2 C3. Now what is this N? Can anyone tell me? What is this N in our case? Okay. I'll tell you what N is, but to try to find the count. Okay. So N is the total number of ways to distribute N. Oh, sorry. How many toys were there? 6 toys among 3 children. Number of ways to distribute 6 toys among the children. So what is N? Can anyone tell me? So how? So can anyone count how many ways can you distribute 6 toys to 3 children?
So it is 28.
How many? Yeah, Shamila. Yeah.
28, sir.
28. Okay. And how did you find it?
Using this formula n plus r minus 1 CR formula.
Yeah. Say it again.
N plus r minus 1 choose r formula we are using, sir.
Okay. Right. So one way to do it would be like n plus r minus 1 choose r.
3.
Right.
Yes.
6 toys. Okay.
Yes, sir.
6 toys, 3 children. And so you need to partition it into 3 parts using 2 sticks. So this is the formula for that. Okay. Good. Uh, that is correct. But that is correct in the setting that all the toys are actually same. All the toys are identical. The question is, what if the toys are different? Are you getting what I'm saying? So what if I label the toys as 1, 2, 3, 4, 5, 6? For the sticks method, um, the first child getting 1, 2. Okay. Okay, this is child 1, child 2, child 3. Okay, this is how you place the sticks now. But it may so happen that 5, 6 is what is gotten by child 2, which is not possible using the sticks and stones method, because as soon as I have sticks here, this is what is for child 2 and this is not for child. I hope you are getting what I'm saying. So this kind of labeling is not possible using sticks and stones. If the stones are not identical, okay, that is all the stones are distinct, then the count will not match. Okay, if Sharmina, if the here instead of different it was written identical, okay, then we can use stars and sticks and stones. In fact, I am glad that you pointed this out, because I was about to ask the same thing. Okay, I was about to ask the same thing. Why can't we use sticks and stones in this case? But good. Okay, so identical. So this causes a problem. So sticks and stones will not give us the correct answer. So if quickly anyone has a suggestion on how to count this, 6 toys among 3 children using a simple argument. So a simple way to do it would be, consider 6 places. Okay, Sharmina, this is close to what sticks and stone does, but slightly different. So let us say these are toys: 1, 2, 3, 4, 5, 6. Now to each toy I can put a nameplate out there. Okay, I can put a nameplate saying that, okay, this toy will belong to child 1, this toy will belong to child 2, and so on. So this toy, putting a nameplate like, okay, this belongs to child 1, this belongs to child 2, this belongs to child 1, this belongs to child 3, and so on. In how many ways can you do that? Well, the first cell, it has 3 choices. Okay, that is, it can belong to 3 children. The next one also has 3 choices. The next one too has 3 choices. And 3, 3, 3, 3. So the answer is 3 times 3 times 3 and so on, which is equal to 3 to the power 6. Which is equal to 9 power 3. What is 9 power 3? Let's see. 9 times 9 times 9. 729. So n is 729. Yeah, I'm glad that you talked about sticks and stones. Because I was going to talk about it anyway. So as you can see, in this particular case, we cannot be using sticks and stones. Okay, when they are different, we cannot use sticks and stones. We need to use this technique. So now it's straightforward. So let's count NC1. NC1 is number of ways in which child 1, Okay, number of ways in which child 1 gets not at least one toy, 0 toy. C1 gets 0 toy, which means if I have 6 places, 1, 2, 3, 4, 5, 6, I have 2 choices each for children 2 and 3, child 2 and child 3, child 2 and child 3. None of these labels will say this belongs to child 1 because child 1 gets 0 toys. What does this mean? NC1 is equal to 2 times 2 times and so on. How many times? 6 times 2 to the power 6, which is nothing but 64. And see that, this is symmetric. So this is equal to NC2 is equal to NC3. Okay. And finally, next is NC C1, C2. Okay. C1 gets 0 toy. C2 gets 0 toys. Okay. So how many ways are there? So I'll think of again boxes with the names of the children who own the toys. So there's only one choice. There's only one choice. And there is one choice and one and so on for child 3. In other words, child 3 owns all the toys. That is, child 3 owns all toys. So there's only one way that this happens, right? Where child 3 owns all the toys. That is, I take all the toys and give it to the child 3. So N C1 C2 is the same as N C2 C3. Okay, because the argument is symmetric. C1 C3, which is nothing but 1. Okay. Finally, N C1 C2 C3. All three children. Okay, get 0 toy. Then how many ways are there to distribute? I mean, then it's absurd, right? How can you give away all the toys if none of the children get any toy? So this is absurd. So this cannot happen. That is, number of ways equals 0. Now all that's left is actually to sum it up. Okay, N C1 bar, C2 bar, C3 bar is equal to this capital N, which is 3 to the power n, 729, minus 3 times 64 plus 3 times 1 minus 0. This is your answer. So 729 minus 3 times 64 is 3 times 64. 192 plus 3. 729 minus 192 plus 3. 729 minus 192 plus 3 is equal to 540. And this is your answer. Okay. I hope it's clear now. Okay. So just to repeat, okay, I'll let you guys try the next question. Okay, just to repeat, always think of the opposite case of the constraint. Okay, opposite case of the constraint. So opposite of at least one toy is 0 toys. So that is a condition. Okay, so the conditions are child 1 gets 0 toy, child 2 gets 0 toy, and so on. We need C1 bar, C2 bar, C3 bar. That is, each of the children get at least one toy. That is what the question is asking, right? And N here is the total number of cases, total number of distributions. Here we cannot use stars and bars. We cannot use sticks and stones because all the toys are not identical, different toys. Okay, and Yeah, and then we just find these quantities using the same logic, finding distribution for smaller sets. Okay. So yeah, please try this question. There are 9 letters having different colors. It is of a very similar flavor. So there are 9 letters having different colors. So let's not solve the problem. I'll just ask you a few questions. Okay. There are 9 letters having different colors. Okay. 9 letters having different colors: red, orange, yellow, green, blue, indigo, violet. So colors of the rainbow. This Vibgyor. Okay. And 4 boxes each of different shapes. So one is like a cube, one is tetrahedron, and so on. There are dodecahedron and so on. Okay, these are the different shaped boxes. And what are they saying is how many ways are there to place 9 letters into 4 boxes such that each box contains at least 1 letter. So you can see that it's similar to the previous problem. What was there in the previous problem? You are distributing toys among children, right? So the toys are now letters, and the boxes and children are boxes here. Okay. Now just tell me, please tell me what is n here, the total number of distributions. What is n here? Total number of ways to distribute 9 letters into 4 boxes. Akanksha. Yeah, good Akanksha. Similar to the previous problem, right? Yeah. So we have 9 letters, R, O, Y, whatever. And for each of them, I put a label. This belongs to box 1, this belongs to box 3, 4, 1, and so on. So each of them have 4 choices and 4 choices each for each box, for each letter, right? So this is nothing but 4 times 4 times 4, okay, 9 times, 9 many times. So it's 4 to the power 9. Good. And now, can you tell me what should be, my conditions C1, C2, C3, and C4? Okay, so can you tell me what is C1? So, yeah, what should be the first, or what should be the conditions? What should be C1, C2, C3, C4? So, if you remember, I told you about finding the opposites, right? So, what is the opposite of finding box 1 has 0
Less
letters?
than one.
Right? Yeah?
Less than one.
Yeah, less than 1. That's right. So, what is less than 1, Bhumika?
Zero shapes.
Exactly. Good. Yeah, Akanksha, 0. Box 1 has 0 letters. Exactly. I mean, because you can't have half a letter or something like that. No? So, C1 is less than 1, or in other words, 0. Box 1 has 0 letters, and box 2 has 0 letters, and so on. So that when we find C1 bar, C2 bar, C3 bar, C4 bar, we actually mean, at least 1 letter, at least 1 letter, at least one. Each of the boxes has at least 1 letter. How many ways are there? And that is exactly what the question is asking. And the remaining, I'm leaving it out to you so that you can solve it for yourself. Okay? Good. Yeah, the remaining is just applying the formula. So we are coming towards the end of the session. Okay, I mean derangement, but it's a rather simple and not too calculation intensive um, part of this discussion. Derangements. Okay, so what is meant by derangements? So derangements can be seen as the opposite of arrangements. Okay, something that is not arranged properly. In other words, it is a permutation where no element sits in its proper position. Okay, that is, this is a derangement. Why? Because 2 sits at position 1, 1 sits at position 2, 3 sits at 4, 4 sits at 5, 5 sits at 3. So um, no object sits at its own position. That is, 2 does not sit at 2's position, 3 does not sit at 3's position, and so on. It sits at someone else's position. Similarly, is this a derangement or not? By the definition, is this a derangement or not?
Not sir. 3 is the same position.
Exactly. Good, Bhumika. 3 is not in its own position. 3 is in its own position. So this is not a derangement. Okay. Good. So this is not a derangement. So the question is counting derangement. You may already have seen in the lectures that counting derangements is really useful. Like counting before we used to count number of bijective functions, number of injective functions, and so on. But counting onto functions was something that was difficult, and you can actually do it using derangements. Anyway, what is the formula of the? Okay, first of all, the number of ways in which n objects derange, that is on distribution. Okay, how many ways do they not fall in their proper place is denoted by dn. Okay, number of ways in which n objects derange is denoted by dn, and this is the formula for derangement. And if you take n factorial common, you get this, and it so happens that this series is something special. Okay, because when you take it for a large enough n, this is equal to 1, almost equal to 1 by e, where e is Euler's number. E is a very famous number. It's like pi, which is 2.718, and so on. Irrational number, which is very famous. Okay, so dn can also be given by this, approximated by this formula. Okay, the more digits until which you approximate e, the better your estimation will be. Okay, and what is 1 by e? It is something like 0.36788. Okay, so the question for derangements, okay, usually is in this flavor. Okay, this is a very famous problem called the hats problem. Okay, question is as follows: 10 people enter a room handing their hat to a servant of the house. Okay, what is the number of ways in which none of the 10 people receive their correct hat if a person hands their hat back randomly? Getting it? So they, like the people actually give their hat to the hat person. Okay, so this person collects all the hats. So he has a huge collection of hats. And they enter this room. While going out, this other person gives them the hat back. But this person is almost blind. He just gives them out randomly, not looking at which hat belongs to themselves. So what is the question? The question is 10 people receive their hat. None of the 10 people receive the correct hat. So this is where you see the derangement, the idea of derangement occurring. Derangement says that the person does not enter the correct house, right? Something like that. So 10 people do not receive their correct hat. Okay. So 10 people do not receive correct hat. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hat number 1 goes to person 2, hat number 2 goes to person 3, hat number 3 goes to 5, 4 goes to 1, and so on. How many ways are there? This is nothing but it is exactly the number of derangements of 10 objects, right? Number of ways in which 10 objects are distributed such that they don't fall into their correct place. So this is nothing but dn, which is equal to n factorial by e, which is almost equal to n factorial by e. So what is n factorial? It is 10 factorial, okay, a rather large number, divided by e, which is around 0.3, what is 3678. Okay, so, and what is this equal to? Let's use the calculator. Is there a factorial? Okay, I don't think there is a factorial function. Oh, there is. Good. 10 factorial, rather large number, okay, divided by 0.36778. So yeah, you can see some 98,066, 98,066, around this, almost equal to this number. So I mean, such a large number of ways in which this can happen. So actually, derangements go to show that, with a very high probability, the correct person will not fall into the correct place. The correct hat will not be given to the correct person. Okay. So, so yeah, there's another question in the same flavor. Please try this question. Okay. The question says, 7 groups in picnic who has brought their own lunchbox, and then the 7 boxes are exchanged within those groups. Determine the number of ways that they can exchange the lunchbox such that none of them get their own. Okay. Seven groups they are saying, but let's say 7 people, each have the lunchbox. And then they exchange with each other. Determine the number of ways that they can exchange the lunchbox, none of them get their own. Can you tell me quickly what the answer is? I mean, you don't need to calculate the exact answer. Just tell me what this stands for, what this denotes. Okay. So, okay. 7 lunchboxes are distributed among each other. And what is the number of ways that they can exchange the lunchbox that none of them get their own? In terms of derangements, it is nothing but the number of ways 7 objects derange. That is 7 objects 7 lunch boxes don't go to their correct owner. It's nothing but D7. What is D7? D7 is just 7 factorial divided by E. Yeah, E. Oh, there was a. Sorry, I made a mistake here. This should be 2 point. Sorry, 10 factorial divided by 2.718. This is E, no? So it's 10 fact. Okay. Sorry. In the previous one, I made a mistake. Point times 0.3618 or something. What's wrong? 10 factorial divided by E equals, okay, some 1334. So in the previous one I made a mistake, sorry. 1334 something. Okay, anyway, here we have 7 factorial divided by E. That is the formula for Dn, right? Which is nothing but 7 factorial, okay, divided by E, which is 1854. And this is your answer. Okay, I mean, if the question is just simply the correct box does not go to the correct owner, then derangement. Use the formula for derangement. Okay, 1854. So, okay, this is one question. Okay, a postman can put 12 letters into their. Okay, I'll demonstrate how to do this question. Then please try the next final question after this. Okay. A postman can put 12 letters into their respective envelopes such that exactly 5 will go into the right envelope. Find the number of ways of doing this work. Okay. So a postman, okay, can put 12 letters into their respective envelopes such that exactly 5 will go to the correct envelope. Exactly 5 will go to the correct envelope. The remaining goes like this, something like this. The remaining goes something like this, not to the correct envelope. So find out the number of ways of doing this work. I'll show how this is done. I'll let you guys think for a while about how to do this. Okay. So and 5 go. The main observation is this: 5 of the letters go to correct envelopes, but the remaining, which is 7 envelopes, go to wrong envelopes. Okay, what does it mean to go to the wrong envelopes? Remaining, that is, they derange. This is the main idea. So all that is remaining is number of ways to choose 5 envelopes. Okay, because those 5 could be any of the 12 envelopes, right? Is 12 choose 5. Okay, number of ways to choose. Okay, it's 12 choose 5, and remaining 7 derange. So number of ways that they derange is d7, which is equal to 7 factorial divided by E, which we saw from the previous question is 1854. Right. So total number of ways in which exactly 5 go to correct envelope is equal to 12 choose 5. First you choose the 5 envelopes, 5 letters that go to the correct envelope, and remaining will derange. So 1854. Okay. Which is equal to 12 choose 5 is something like, oh, okay, so this is something like until 7, 12, 11, 10, 9, 8 divided by 5, 4, 3, 2, 1. Yeah. So 4, 3 is 12 and 5, 2 is 10. Okay, 11 times 9 times 8. 11 times 9 times 8 is 792. 792 times 1854. So 1468 368. Okay, there's a problem with this. 5 envelopes. I think there's a problem in calculating this. So if 12 choose 5, is this correct? Okay, I'll just 12 factorial divided by 5 factorial times 7 factorial. This is what it is. So 12 factorial divided by 7. Oh, okay, I don't think this calculator will be able to. Times 5 factorial equals, oh, it's showing 792. Okay, this should not be proper, but okay, I'll think about that later. But meanwhile, please try this. Okay, but the total logic is the basic logic is this: you choose the correct 5 envelopes. Okay, and then what you do is, um, the remaining will derange. The remaining will not go to the correct spot. Okay. So yeah, the final question about for this session is the following. Please read this and please try this. Okay. A school organizes a game where 100 students, okay, are grouped into two sets of 50 students each. Each student in a group is assigned a number from 1 to 50. Before the game commences, the two groups are kept on either sides of the field. Once the game begins, the students need to find the correct partner. That is, the student in the opposite group with the same number assigned in 1 minute. So in 1 minute, okay, the student needs to find their partner in the opposite group. Okay. In how many ways can the game end with exactly 25 correct pairs of students? Can you try this? It's a very similar logic. Okay. You don't need to tell me the final answer. Don't need to tell me the final answer. Just because I'm sure the final answer will be just too large. Okay. But look at this question, stare at it, and try to use the same logic we used previously. Somewhere we need to use the idea of derangements. Okay, Akanksha says 50C25 times P25. Huh. Okay, Akanksha. I mean, the logic is correct, but I think there might be a slight error. The direction is correct, okay. 50C25. So which students actually derange? That can, and this is the hint. Which students will actually derange? So can you check your? In other words, like the derangement, okay, Akanksha, the derangement is it for the incorrect pair of students? Is it for the correct pair of students or for the incorrect pair of students?
Sir, incorrect pair.
Exactly. And how many? Oh, okay. Um, yeah, I think I am wrong. Sorry. We are talking about pairs, right? Yeah, that's right then. Akanksha, yeah, that's right. That's good. Incorrect pair. Exactly. But since we are talking about pairs of students, it will be equal on both sides. Correct. That's right. Um, okay. So I is the rest also fine? Yeah, Akanksha's answer is correct. It is 50C2 times D25. Why? So let's say this is the field, okay, and there are 50 students here and 50 students here, and there is a student labeled 1, there is a student labeled 1, 2, and there's a student labeled 2, labeled 3 is here, labeled 3, and at the start of the game all the students will rush to the middle, okay, and 2 should find 2 and 3 should find 3. Okay, and at the in 1 minute they should do it in 1 minute. It may so happen that one meets some 5, and this is incorrect. This is an incorrect pair. Okay, so in other words, they are saying exactly 25 correct pairs of students. So 50 here, 50 here. So 25 exactly meet whoever whoever their partner is. Okay, or I think showing it this way is better. And the remaining actually derange. So number of ways to choose 25 pairs, okay, 25 pairs from 50 pairs is 50 choose yeah, 50 choose 25, and the remaining 25 pairs derange, meaning that remaining 25, yeah, pairs is fine, I think, meaning 25 students from here, okay, do not meet the correct partner from this the right side. Let's say A and B. So 25 students from A do not meet the correct partner from B. So which is nothing but that is B 25 ways. So final answer 50. Okay, 50 choose 25. Okay, this is for the correct pairs, and the remaining, okay, will derange. The remaining can arrange themselves, derange themselves. Okay, not go to each other in 20, 25. By the way, why should they derange? Why should they derange? No, why? Because if even one student from the remaining 25 had gone to the correct place, then this count would be messed up. Then there would be more than 25 pairs which are correct. Okay, so this is your answer. Okay, and it turns out the mistake here was in 798. Is it 798? I actually um, checked 12 choose 5. Oh, it's 792. Oh, then it was correct. 792. Where was the mistake? This is 1468368. Then probably there's a problem with the options. Because the calculation looks correct. Okay. Yeah. Anyway, yeah. So Akanksha's answer is correct. Okay. So that brings us to the end of the session. Okay. I hope you learned to appreciate the application of inclusion exclusion principles, and there are countless applications of inclusion exclusion principles. Okay, it is used in all the ways in modern mathematics. So yeah, that brings us to the end of the session. Okay, hope you enjoyed it, and we'll see everyone in Tuesday 6 p.m. Okay, next week. And if you have any questions, then you can just let me know. But if you don't, then you are free to leave. Okay. Yeah. Thank you, Akanksha. Bye.
Thank you, sir.
Okay. Thank you, Sharmila. Thank you, Divya. Okay. Bye. Okay. Thank you.